are a very common two-part question, which is basically to draw the product of each reaction, and secondly, to describe the relationship between the two products. So the enantiomers, diastereomers, the same, are they constitutional isomers? So it's going to basically ask you to take the concepts you previously learned in your stereochemistry chapter and apply them to alkenes. Okay, so let's hide these bottom three examples right now. And let's look at this first reaction here. So here we're looking at a hydrogenation reaction, palladium on carbon, and we're adding hydrogen. So what are we going to do here? We're going to break the carbon-carbon pi bond, and we're going to form a new carbon-hydrogen bond. So if we previously had one hydrogen here, let's say it's blue, we're going to have a new carbon-hydrogen bond. Let's draw this in red. And so our final product is going to look like this. If you'll note that it doesn't actually matter for us whether this new red hydrogen is a dash or a wedge. In other words, it doesn't matter what face the hydrogen adds to. This is not going to form a chiral center here, and therefore we're not going to have the possibility to form enantiomers, diastereomers, or constitutional isomers because we're not forming a stereocenter. This is going to be very important for this question. Always be very alert to the possibility of forming a stereocenter. Here, this is actually the only product that we can form from this reaction, no matter what. And actually, we don't have a stereocenter present at all. This is an achiral molecule. Okay, let's look at the second question. So in this example, we're adding BH3 to our alkene. So initially, we will form BH2, and we'll have our CH3 here. Now, the hydrogen that we're adding could either be a dash or a wedge. In fact, it doesn't really matter. Once we do the oxidation step, so part 2, hydrogen peroxide and NaOH, we're going to turn our boron into an OH2. Oops, OH. So that would give us this primary alcohol here. And again, another situation where we're actually not forming a stereocenter, no matter what face we add. So we're just going to actually end up forming the same. So same for the top one, same for this next one here. Okay, let's try this next example. Now here we actually have two possibilities, two faces that our first intermediate, the bromonium ion, could add to one of two different faces of this alkene. So let's draw both possibilities here. We could have bromine, a bromonium ion as a wedge, and we could also have bromonium ion as a dash. So wedge, okay. And so then the next step is going to be the counter ion, the Br minus, coming in and attacking from the back on either side. What this will do is result in us forming, in the top case, we're going to have inversion of stereochemistry on this carbon. So we're going to end up with a dashed bromine, and we're going to have inversion of stereochemistry on the right-hand side. So we're going to actually end up with a wedged bromine here. And so when we compare these two molecules, now notice that this stereocenter, we are forming a stereocenter, first of all, very important. It's attached to bromine, hydrogen, which I didn't draw in, here it is. CH2Br and this carbon with a methyl group is different from, so this is a chiral center, and likewise, so is this. These two chiral centers have the opposite configuration. However, we might ask, how are these two compounds related to each other? You might want to say initially they might be enantiomers. But if they were enantiomers, they would have to be complete mirror images in every respect. And notice how this stereocenter here, we have a stereocenter, this carbon attached to the methyl group, methyl, H, ethyl, and the carbon with all the carbons with the bromine. This is a stereocenter as well as this is as well. So this has the same configuration in both cases. And in fact, if you're to figure out R and S, this would be an R configuration on this carbon, an R, And I believe this is an R here, and this is an S. And if you note two molecules which are identical in every other respect, and that includes having a bromine on the end, and their stereochemical configurations are not exact opposites of each other, they differ by, they have at least one that are the same, they are going to be diastereomers. So that is the relationship between these two molecules here. They are diastereomers. Okay, now let's look at this last example here with palladium on carbon and deuterium. If we draw the product out of this reaction and think about the different faces that deuterium, D2, could add to, we could have a wedged deuterium and a dashed hydrogen. This would be CH2D. So notice we're forming a stereocenter here. It's got 4 different groups present. On the right-hand side, this is not a stereocenter. So we have stereocenter here, and then what would the other one look like? Well, it would be the opposite configuration at that carbon. So we would have CH2 deuterium. We would have, let's draw this as a dash, draw our H as a wedge. Okay, now notice how, again, these two stereocenters are opposites of each other. However, this stereocenter has not changed. So this has the exact same configuration for both cases. So therefore, they cannot be enantiomers of each other. In order for enantiomers, they have to have the opposite configurations at all their stereocenters. So again, these must be diastereomers. So those are fairly simple examples, but it gives you a taste of the types of questions that you could get asked in this realm. The most important lesson to absorb from this question is just to pay extremely close attention to whether your reaction is forming a stereocenter. It's a very common situation for alkene reactions. Pay very close attention to whether your reaction is forming a stereocenter, because you very well might be asked whether or not your products are enantiomers, diastereomers, constitutional isomers, and so on.